There's actually two ways to do this problem. There's one way the book shows us, and then there's another way that we actually end up using in calculus. So first off, the way the book shows us is that we have this, and we're going to change our limit to f of x plus h minus f of x divided by h. That means this x plus h, I have to plug that in everywhere that I have an x into the function that's given for us, and the function that is given is 12x squared minus 6x. Now there is a we should get kind of good at the perfect square trinomial, because we end up using that a lot if we're going to do it this way. So rewriting this problem, I'd have and I'm not using correct documentation here because we're doing a derivative, but anyway, so I'd have 12x plus h squared minus 6x plus h minus 12x squared minus 6x over h. Now what happens is with this is that this problem is going to, this first part, so I have the 12, the expansion of that is x squared plus 2xh plus h squared. Here, this negative 6 is going to go in to both of those, so I'd have negative 6 x and negative 6h. Now here, this is the tricky part, this negative here, is that I distribute that in there, so I'd end up with negative 12x squared and positive 6x all over h. Now, I'm going to go ahead and simplify some of this. 12x squared plus 24 let's fix that. 24 xh. And so instead of h, sometimes we use the delta sign as well. Plus 12h squared minus 6x minus 6h minus 12x squared plus 6x. Now this starts to get a little bit confusing, just with all these different variables and this stuff. But now I can simplify a lot of this. I have a 12x and a negative 12x squared. Those cancel. I have negative 6x and positive 6x. Those cancel. Now, the part that we don't need, or before we even do that, so now we're going to look at what we have, and we're going to simplify the top and bottom. Since all of my remaining terms have an h in them, I can divide that out by the one on the bottom. So I'd be left with 24x plus 12h minus 6. Now I plug in 0 for h, which means this part here would drop out. So I'd be left with 24x minus 6. Now this is the equation I would use to find my limit, and so I'd be plugging in whatever number is given that we were trying to find the limit for, and that would be my solution. Now the other way to do this that is not shown in the book, and can be a little bit more complex just at first, but this is going to be the way that we actually really do it, and I said a little bit more complex, but not really. If we have terms, and I'll just give, so say we have ax n plus bx. What I can do is that the derivative of this is going to be equal to, and I'm actually going to cut this last part off because I can do it for each individual one. What the derivative is going to be equal to is a times n x, and the new exponent would be n minus 1. So with the one we had here, it makes it pretty easy. So just for this term, the derivative of that, just that part, would be 2 times 12, and the new exponent would be 2 minus 1, which gives me 24x. So for the other part of that, that was minus 6x, I'd have an exponent of 1. So I'd have negative 6 times 1, and my x would be 1 minus 1, which is 0. That means that x is gone. So I just have negative 6. And for what we're doing, that'll probably work for almost all of them. It doesn't work with division because there's a different property with division, unless we have, if we have division, say we have 2, we have x to the third, I would need to change that to 2x to the negative third power, and from here I could still use that. I'd do 2 times negative 3 would be negative 6, x negative 3 minus 1, so it'd be negative 6 x to the negative 4, which is the same as negative 6 over x to the fourth power.